Hey there, it's Shannon Magic Myers, and today we'll be looking at properties of matrix operations. So let's get started with this first theorem 2.1, properties of matrix addition and scalar multiplication. So if A, B, and C are M by N matrices and C and D are scalars, then the following properties are true. So first off, the sum of two matrices is commutative. So A plus B is equal to B plus A. Let's do a little proof of this. Let me get a smaller pen size here. And how would we do this? Well, we don't know all of these properties for matrices, but we do know these properties for what? Beautiful. The real numbers. So again, just like with the vectors, the whole evil plan is to get things in terms of the real numbers, whether you have to combine more than one matrix to make one happy matrix and then use the real numbers, and then you break them apart again. So it's very similar to all the vector stuff. In fact, guess what? Matrices are vectors. Don't tell anyone. All right, here we go. So for all of these, let's have a basic starter, okay? We're going to let A equal to Aij, B equal to Bij, matrix C equal to Cij, such that Aij, Bij, and Cij belong to the real numbers for 1 less than or equal to I less than or equal to M. Good, because there's M rows. And 1 less than or equal to J less than or equal to N, because we'll have N columns. We're also going to let C and D belong to the real numbers, so they'll be our scalars. Groovy? Okay, so given that we have all that down, let's go and see what we get here on our proof. So starting with the left-hand side, we get A plus B equals. Well, that's going to be in representative element form, Aij plus Bij. Good so far? Now, I want to bring these to be one happy matrix so I can use the properties of real numbers on them. So this will be Aij plus Bij in one matrix. Now that I have them in one matrix, what can I do? Awesome. I can commute them because the set of real numbers is commutative. Cool, cool. So these are the rationales. This is a definition of matrix addition. Do it like this, I guess. This one is because the set of real numbers is commutative. And then what can we do now? Awesome. Break them apart again. So we'll have representative element Bij plus Aij, which is B plus A. So this one again is by definition, this last one here, definition of matrix addition. Groovy? All right. The next one I'll leave for you guys to prove, but it turns out that matrices are associative under addition. So A plus quantity B plus C equals quantity A plus B plus C. Now, matrices are also associative under multiplication, all right? Scalar multiplication. So C times D, that quantity times A, is going to be equivalent to C times quantity D times A. So we'll go ahead and prove this one. What we'll have is C times D times the matrix A is equal to C times D, and then we'll put A in terms of the representative element, Aij. Now that's going to equal to the one happy matrix where we have quantity C times D, and then times each representative element. Good so far? And what would that be under? Beautiful. This is definition of matrix scalar multiplication. All right, moving right along, what's going to happen? This is going to be equivalent to the matrix, awesome, C times quantity D times Ai, J, and that is because why? Awesome, you're amazing. The set of real numbers is associative. Okay, moving right along, what will we get now? This will be equal to C times the representative element D Aij, and that would be because, good, definition of scalar multiplication for matrices. And then what else do we need to do? So now we have our C outside, and now we can use that property or that definition again and write D times the matrix A as a representative element. And so both this one and this one are by definition of scalar multiplication for matrices. And then this will equal to C times D times matrix A. Cool, cool? Actually, I don't need to put it in that format. I can do regular parentheses. And that's what we wanted to show. All right, so next up, 1 times A, what do you think that's going to equal to? Let me clean this up a little bit. So 1 times A is equal to, you got it, A, all right? And that's the multiplicative identity for scalar multiplication. And a scalar times quantity A plus B is equal to, awesome, C times A plus C times B. So let's do the proof of this one too. So now we start with our left side, very good. So C times quantity A plus B equals C times quantity, and we'll put it as a representative element, Aij plus, and then another representative element, Bij. Now, what's going to happen? You can't use the distributive property yet, so if you feel like it, slap your hand. What you need to do is what? Awesome. Make one happy matrix as a representative element. Okay, so you'll have Aij plus Bij within the matrix, and that is why. Awesome definition of matrix addition. So now what will we do? we can bring that scalar in, and you have to be careful. You have to keep the grouping. So C is coming in and it's multiplying to Aij plus Bij in parentheses. And so they'll all be in that matrix. And that is why. Awesome. Definition of matrix scalar multiplication. Okay, next up, what should we do? Awesome. The real numbers are distributive over addition, right? So this is going to be Caij plus Cbij inside the matrix. And so the rationale for that is because the set of real numbers is distributive. Over addition. And next up, what do you think we should do? Awesome. Now we'll separate these. So we'll have C times Aij as one matrix, and then plus C times Bij as the next matrix. And why is that true? Very good. Definition of matrix addition. And now, where do we go from here? That will give us, beautiful, C times Aij, so we can take the C out, plus C times Bij. And that was why? Good. Definition of matrix scalar multiplication. And then, lastly, we'll have C times A plus C times B, which is what was to be shown. Groovy? Okay, now number 6, the quantity C plus D times the matrix A is equal to C times A plus D times A. That's the distributive property again. And then we come to our first example. So go ahead and pause the movie and work out these problems without using the graphing calculator. And then what I'd like you to do is just kind of think to yourself, what are you combining, right, to do these problems? Are you changing them around using properties? You know, we use these properties all the time, but we don't even think about it. It's so normal to us. So anyway, good luck. Okay, let's see how you did. So for our first one, I like how it's written. I think that grouping A plus C, those matrices will be good. So this will end up being C is -2, right? And then we'll have what? Matrix A is this one going across -3, 5, 3, 4, and 4, 8, plus C, which is -7, 1, -2, 3, and 11, 2. So we will get -2 times the matrix, what? Awesome. -3 plus -7 is -10. 5 plus 1 is 6. 3 plus -2 is +1. And then 4 plus 3 is 7. 4 plus 11 is 15. And 8 plus 2 is 10. How'd you do? Good, good. And then our last step for this one will be bringing in that -2. So we'll have 20, -12, -2, -14, -30, -20. Good so far? Awesome. All right, let's see what happens with this next one. So for this one, personally, I would do the C times D first. So we would have C is -2 and D is 5. They're both scalars. And then I want to multiply that to matrix B. So notice that the brackets in the first part are just grouping symbols, whereas the bracket in the second part that I'm doing now represents a matrix. So it's really in the context in which you're looking at it. I know these are just two scalars in here, okay? All right, so here we go. Matrix B is what? 1, 1, 2, 7, and 6, 9. So that's going to give us what? -10 times the matrix B, which is -10, -10, -20, -70, -60, and -90. Cool, cool? All right. And lastly, what do we have here? C times A minus quantity B plus C. So what was C again? C was -2. So we will have -2 times A, which is -3, 5, 3, 4, 4, 8. And then minus this sum of matrices. So B plus C, this was B, I believe. And C is -7, 1, -2, 3. And 11, 2. I'm just going to double check that I did matrix A correctly. Yep. All right. So here we go. This will give us, I'm going to bring that -2 into matrix A. That'll give us 6, -10, -6, -8, -8, and -16. Minus, I'll make one big happy matrix here, and this will give us -6, 2, 0, 10, 17, and 11. And then we'll have an end result of 6 minus -6. Remember, it's like adding the opposite, right? So you'll end up with 12. -10 minus 2 is going to be -12, -6, -18, -8 minus 17 is going to give us -25, and then -16 minus 11 will give us -27. How'd you do? Awesome. If you have your zero matrix, the assumption is that the dimension is such that it is defined for addition. Okay? So, here we go. Some matrix plus the zero matrix is just that matrix. So what does that mean? The zero matrix of the same dimension is the identity element for A ends up resulting in the zero matrix. So a lot of times you'll see this denoted in the book, like a textbook, you'd have it 0 in bold, right? You can also do something like this if you want. You can write 0 as the representative element, and then you could say M by N. Okay? A lot of times people just write 0, or they write 0 like it's a vector, okay? And then people know from the context. So for right now, I guess I'll just do it this way, and then we'll go from there, all right? So if C times A equals the 0 vector, then what do you think must be true? What do you think? Well, then C either has to be the scalar 0 or A has to be the m by n 0 vector. Cool, cool? And both could be true. So I guess we could say and or, right? All right, so let's take a look. Solve for x in the equation given that A equals -2, -1, 1, 0, 3, -4, and B equals 0, 3, 2, 0, -4, -1. So this matrix X is equal to 3 times A. So if you don't mind, I'm going to go a little faster. I'll just bring my scalar in right off. So 3 times A would give me -6, -3, 3, 0, and 9, -12. Cool, cool? All right, and then we're going to be adding, and then I'll bring a -2 in here. So -2 times 0 is 0, -2 times 3 is -6. Then we'll get -4, 0, +8, +2. All right. So just so you can match everything up, 3 times A is this matrix, and -2 times B is this matrix. And then we just need to add them to get our matrix for X. So that'll be, we'll have -6 plus 0 is -6. -3 plus -6 is -9. This one will be -4. We'll have a 0 here. And then 17 and -10. Cool, cool? All right, there we go. How'd you do? Awesome. Next up, we have 2 times A plus 4 times B is equal to -2 times X. Okay, so first of all, this is reflexive, right? So we can just say that -2 times the matrix X is equal to 2 times the matrix A plus 4 times the matrix B, just getting, you know, the matrix X on the left side. Now what could I do? I could multiply both sides by -1/2, right? So then I'll have X, 1 times X, which is X on the left side, is equal to -A plus -2B. Groovy? All right, so completing this, let's see what we get. -A is going to be 2, 1, -1, 0, -3, +4, and then -2 times B will be 0, -6, -4, 0, +8, +2. Cool, cool? All right, so then X will equal to 2, -5, -5, 0, +5, and 6. How'd we do on this one? Awesome. Okay, so just so you can match it up, we're going to have our -2 times B was this matrix here. And we have -A is this one here. All right, so next up we come to some more properties. All right, so properties of matrix multiplication. If A, B, and C are matrices with sizes such that the given matrix products are defined, and C is a scalar, then the following properties are true. So I bolded that part for a reason, okay? Given that the dimensions work out and you can multiply these three together, matrix multiplication is associative. So A times quantity, B times C would equal to A times B, that quantity, times C. A times quantity B plus C would equal to what? Beautiful. A times B plus A times C. When the dimensions work out, then matrix multiplication is distributive over addition. All right. So then over here, same idea. A times C plus B times C. And then scalar times a product, AB, is equal to the scalar times A, that quantity, times B, which happens to also be equal to A times C times B. Cool, cool. All right, so here we go. Show that A times C equals B times C, even though A does not equal B. So what I'd like you to do is pause the movie and try doing the multiplication by hand to make sure you can do it on the exam. You can definitely double check your result using the calculator or Octave or whatever you're using. So either pause the movie, work it out yourself, and then check your result, or work with me. Here we go. A times C is going to be equal to, so A is 1, 2, 3, 0, 5, 4, and 3, negative 2, 1. And then C is equal to 0, 0, 0, 0, 0, 0, 4, negative 2, 1. Amazing, isn't it? You see that neither one of these matrices is the zero matrix, right? And A is not equal to B, but A times C is equal to B times C, which is pretty cool, right? That's A times C, and then this is B times C here. So they're equivalent. Actually, let's not highlight these. Groovy? Okay, so let's see what we have next. Another one where I'm getting you to believe things by working things out. So show that A times B equals the zero matrix, even though A is not equal to the zero matrix and B is not equal to the zero matrix. So here we go. Let's do it. A times B is equal to 2, 4, 2, 4 times 1, negative 2, negative a half, and 1. That will equal to cool. All right. Next up, a theorem, properties of the identity matrix. Since A is M by N, you're going to need to have an N by N identity matrix. So the identity matrix, just to show you, like I2, it's going to be the diagonal matrix that has ones down the main diagonal and zeros elsewhere. And when you have a little 2 down there, it means of order 2 or a 2 by 2. And so what do you think I3 would look like? Beautiful. Ones down the diagonal, zeros elsewhere. What would IN look like? Well, let's check it out. So for IN, what would we have? We'd have 1, 0, dot, 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 all the way down, zeros. right? And then you'd have a 0, 1, 0, dot, 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 0. And then this one would continue down like so. We'd have all zeros. You'd have a 0 underneath here, and then it would go down all zeros. And then what are we going to have here? I mean, this one, these ones are going to go on all the way down to the corner. And then these would go as zeros. And these would go until you're right before the 1. You'd have a 0. Sorry, these are kind of big dots. Dot, dot. Cool, cool? All right, so it turns out that A times IN is equal to A, and IM times A is equal to A. And the reason the subscript is different is because of the order of the multiplication. Cool, cool? All right, so theorem 2.5, the number of solutions of a linear system. We've had this before. You help me with it, okay? Ready? For a system of linear equations, precisely one of the following is true. The system has exactly, ding, 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 yes, one solution. The system has, yay, infinitely many solutions. Or the system has no solution. Groovy? All right, so here we go. The transpose of a matrix. The transpose of a matrix is denoted A and then a superscript capital T. That's the command in the graphing calculator. In Octave, just a note here, which of course is our free MATLAB. So A transpose would be kind of like an A prime, or you could write it as trans and then parentheses A. So here we go. The transpose of a matrix is denoted A T and is denoted A sub T and is formed by writing its columns as rows. Cool, cool. In general, you could say something like, if A is equal to, in representative element form, Aij, then A transpose would equal to Aji. Cool, cool? All right, so find the transpose of this matrix. Well, what do you think? Good. A is of dimension, or of size rather, 3 by 2, right? 3 rows by 2 columns. So A transpose, when we switch those, is going to be 2 by 3, okay? So writing its columns as rows, we would have 1, 2, 4, -1, 9, and 10. Cool, cool? All right, what about this guy? So A transpose would equal to what? So the first column is 6, -7, 19. So we'll go across. Second column is -7, 0, 23. And third column is 19, 23, -32. Huh, what do you notice? Give you a tricky one. It turns out that if A equals A transpose, A is symmetric. We'll be looking more at symmetry of matrices later. Cool, cool? Okay, so here we go. These were the answers. transposes, right? So again, I'm gonna get our, proofs ready to go so that we don't have to rewrite what A and B are each time, okay? So if we let A equal to Aij, B equal to Bij, such that Aij and Bij, such that Aij and Bij belong to the real numbers. We don't know, what they're bound by, what I and J are bound by. So we'll just keep it simple here. And then we also want to let C belong to the real numbers since it's a scalar. Cool. All right. So number one, it turns out that A transpose is just A. Okay, so A transpose, what would this equal to? Well, if I put A in terms of a representative element, right, I would get Aij for my A. That would be transposed. And then I'd have another transpose out here. Good so far? Well, what's that going to equal to? That's going to equal to, good, Aj, and that's going to be transposed. And what's that going to be? Beautiful, Aij. And that's what we had to show. Cool? All right. It turns out that the sum of two matrices transposed is equal to the sum of the transposes. So let's take a look, all right? So A plus B transposed is equal to, putting them in terms of representative elements, we'd have Aij plus Bij transposed. So that would end up being Aij plus Bij in one happy matrix transposed, which would be Aj plus Bji, applying the transpose. Cool so far? Which in turn is A transpose plus B transpose. That's what we wanted to show, all right? And again, this one here was just by definition of matrix addition, doing that part. Okay, so next up, it turns out that if you have the quantity a scalar times a matrix and then you transpose that, it turns out that you get the scalar times a transpose. And then if you have, be careful, if you have a product AB and you transpose it, you're going to end up getting B transpose times A transpose. They swap, okay? So here we go. Let's do an example. We want to find A transpose times A and A times A transpose. And we want to show that each of these products is symmetric, right? So for this one, I think we should go ahead and utilize some technology. Okay, let's do this thing. Let's go into the matrix menu. I'm going to go and edit. I'll go ahead and edit A. And then I've got a 5 by 4. And let's see what happens. I have 4, negative 3, 2, 0. Oh, that's a 4. 4, negative 2. Nope. -3, 2, 0, 2, 0, 11, -1. And then third row, -1, -2, 0, 3. Fourth row, 14, -2, 12, and -9. And our fifth row, 6, 8, -5, and 4. Cool, cool? Okay, so we'll quit out of there. And now, here we go. Just so you can find out how to only get a transpose, all you would do here is you go into second matrix, and then we would want to go to math. And do you see number 2 is this transpose thing? So we're going to put names first. So we're going to just enter A in there. And then what we want to do is go back into matrices, math, and then go to our transpose. And then let's do enter. And look, we got our transpose, and it has dimension, beautiful, 4 by 5. Okay, so let's do the multiplications. Ready? I'm going to hit second entry. That'll give me my A transpose back, and then times, and let's go to our A. And see what we get. Beautiful. So here we have the two products right next to each other, and notice for the first one, do you see that it is indeed symmetric? So if you were to look at this, you've got like these 10s are the same, right? And then here the 168s are the same. Cool so far. And then here you'd have the -107, and then you have a -70, and then you have -70 and 107. Cool, cool. And then on this one, you've got your 44. Then you've got this 139. And then I'm going to go ahead and do this one in a different color. So all of those entries have that symmetry. Okay, and then what about over here? Let's see. Yep, we got this one, 30 and 30, and then 2 and 2, and then 86, -5, -5, 86. -10, 169, 169, and -10. -47, -37, -37, -47. Running out of colors here. Let's see. -10 and -10, -28 and -28. And the ones that are left are along the diagonal, right? So your diagonal entries are these here that I'm highlighting. And on the first one, these are the diagonals. Cool, cool? All right, so if you folded these matrices in half, they would the numbers would land on top of each other. You'd have the same. Groovy? All right, so let's look at This is very groovy. So now let's look at example 7. A square matrix is called skew symmetric when A transpose equals negative A. Prove that if A and B are skew symmetric matrices, then A plus B is skew symmetric. So at the end of the day, and this is something that you can put, but you have to be careful because you never want to assume what you're proving. So we're going to do a direct proof, and our evil plan we want to show that. So instead of just A, we're going to be doing A plus B. So we want to show that A plus B transpose is equal to negative quantity A plus B. Okay, so that's our little evil plan. And it's fine to put that, on the side. But you have to be very, professional here, all right? So when we do our proof, so we've already, in the premise here, we already know that our premise is that if A and B are skew symmetric matrices, that's the premise. So A and B are skew symmetric. It's an if-then. So premise, A and B are skew symmetric matrices, okay? And so here we go. They've been given as skew symmetric. We can assume that to be true. So we can say A plus B transpose equal to A transpose plus B transpose. Good so far? What is that by? Property of transpose. All right, and then next up, what should we do? Well, what is A transpose? Beautiful, negative A. And B transpose is negative D. And that's because A and B are skew symmetric. That was in our premise. All right. Well, what can we do? I mean, we could factor out a -1, right? Or a negative, and we would get A plus B. And that is because why? Matrices are distributive. Because we did a scalar times, we took, we have a -1 times A plus -1 times B. We factored out the -1. All right. And now we're done, right? That was what was to be shown. Cool little proof. That would be definitely one you might see on an exam. Okay, so now let's go to stochastic matrices, very relevant in the real world. So many types of applications involve a finite set of states. And so this set of states, we call them S1 for state 1, S2 for state 2, etc., down to state N, so Sn, of a given population. The probability that a member of a population will change from the jth state to the ith state is represented by some number, capital Pij, where 0 is less than or equal to Pij is less than or equal to 1. So a probability, that's a probability, right? Pij is. A probability of 0 means what? Good, that the member is certain not to change from the jth state to the ith state, whereas a probability of 1 means that the member is sure or certain to change from the jth state to the ith state. Cool, cool? Okay, so P is called the matrix of transition probabilities. At each transition, each member in a given state must either stay in that state or change to another state. Therefore, the sum of the entries in any column has to be what? Good, 1. All right? This type of matrix is called stochastic. An n by n matrix P is a stochastic matrix when each entry is a number between 0 and 1 inclusive. Okay? So, and again, that column, the sum of any entries in a column has to be 1 as well. All right, so in matrix A, what do you think? Is it stochastic? Well, all the entries are between 0 and 1, so we're good there. And if I add, so like this is our, we could call this our P1 and our P2 if we want, right? And so P1, column P1 sums to, good, 1. Column P2 sums to 0.95, right? Which is not 1. So we would say A is not stochastic. Cool, cool? All right, so B, so we have, now 3 columns, and summing them, what do we have? 1/8 plus 4/8 is 5/8 plus 3/8 is 1. And then 6/10 plus 1/10 plus 3/10 is 1. I'm getting a common denominator in my head. 1/12 plus 4/12 is 5/12 plus 7/12 is 1. So B is a stochastic matrix. Okay? All right. Let's take a look at an example. Aren't you excited? All right. So here we go. A medical researcher is studying the spread of a virus in a population of 1,000 lab mice. During any week, there is an 80% probability that an infected mouse will overcome the virus. And during the same week, there is a 10% probability that a non-infected mouse, will become infected. 100 mice are currently infected with the virus. How many will be infected, A, next week, and B, in 2 weeks? So, okay. Let's just kind of break this down. There's a lot going on, right? So, first of all, we need to find our transition matrix P. Good so far? So, if we want to think of P equal to this matrix here, and it's got these different states, okay? So it can be infected or non-infected. And then it goes across like that too. So infected, non-infected. So the entry in the first row, first column is going to be a mouse that started off infected, stayed infected. Okay. First row's second entry would be a non-infected mouse. It started off well and then it got sick, so it switched to the infected state. Okay, and so we can just put these little in general deals. So, whoops. So for our general setup, this would be P11, P12, P21, and P22. Cool, cool? All right. So now that's our general format. We need to figure out what we start with, like our initial matrix. So there's different orders you can go in this. Let's continue on with P and get the transition matrix and go from there. Okay, so what information have we been given? So again, I'm going to make our grid so we can keep track. So here we go. During any week, there is an 80% probability that a mouse that starts in the infected state will get well, become non-infected. That's what this first one is saying. Okay, so starting infected and then switching to non-infected, right, would be in the what? What do you think? It's got to be in the second row, first column, because this here, this value here, 0.8, which is 80%, means that we started infected and then we switched to non-infected. Cool, cool? All right. So next up, what do we have? We were also informed that during that same week, there is a 10% probability that a non-infected mouse will become infected. So it'll go from being well to sick, right? Well, if it starts off well and it ends up sick, what must have to be true? Beautiful. It would start non-infected and then it would switch to infected. Cool, cool? And so that's where we got that information. Now, how do I get the other two? Well, I know each column has to sum to 1, right? And so this one has to be 0.2 and this one has to be 0.9 in order to get these columns to sum to 1. Groovy? Awesome. So now we need to have like our initial situation going on, right? So again, if we continue infected, non-infected, right? Our x0 is going to be equal to this column matrix. And it said we had what? How many mice? Good, 1,000 lab mice, right? And then, okay, how many start out being sick? Beautiful. 100 mice are infected. And so if we do, our breakdown here with non-infected and then we had infected as the first one, then what's going to happen? We were told that 100 mice were infected currently, so that means that 900 mice must have started off well. Cool, cool? Okay, so now let's take a look at what we have going on here, all right? So we have, part A is asking us, how many mice are going to be infected next week? So these are weekly things going on. Our time frame is a week. So next week, it would be what? P, right? Our transition matrix times our initial state matrix. And that's going to end up being, let's see. So 0.2, 0.1, 0.8, and 0.9 times 100 and 900. And then doing the multiplication on that, what do we get? Well, we have a 2 by 2 times a 2 by 1. So we're going to end up with a 2 by 1. So we'll have 0.2 times 100 is going to be what? 20 plus 0.1 times 90 is 90. So 20 plus 90 is 110. And then 0.8 times 100 is 80. And 0.9 times 900 is going to be what? 810. So when I add those, I'll get 890. Now this is going to be our x1. Good so far? Okay. Now if you keep going on this, I mean, let's do part B. Part B is saying, hey, what about the next one? What about the next week, right? Well, you'd have P times x1, right? But isn't that equivalent to P times quantity P times x0, right? But isn't matrix multiplication when everything is defined, right? Isn't that gonna be associative? So you'd have P times x0. And wow, look at that. That's gonna be P squared times x0. Cool so far? All right, well, let's do it that third way and see what happens. So P squared times x0 equals, well, our P is 0.2, 0.1, 0.8, 0.9 times P, 0.2, 0.1, 0.8, 0.9 times x0, which was 100 and 900. Cool, cool. Well, that's going to be equal to what? 0.2 times 0.2 is 0.04 plus 0.08, so that would be 0.12. And then the next entry is going to be 0.02 plus 0.09, 0.11, and then 0.16 plus 0.72 is going to be 0.88, and let's see, 0.08 plus 0.81 is going to be point what? 89. And look at that. Do you see? You still have a stochastic matrix, right? Because each of those columns add up to 1. And so now multiply that to 100, 900, and let's see what happens. Okay? So that's going to end up being equal to 12 plus 99 is going to be 111. And then 88 plus 801 is going to be 889. Cool so far? So let's put official results here so we have some sort of a conclusion. In this first one, we would answer next week 110 mice will be infected. And then for the second one, what did we find? In 2 weeks, 111 mice will be infected. All right, what do you think is going to happen? I mean, let's check this out on the calculator. I'm going to do our transition matrix as matrix A, okay? So what was that? It was a 2 by 2. And then what do? We had 0.2. It enters it as 0.2, so make sure you look at it carefully. 0.1, 0.8, and 0.9. Cool, cool? So I'll quit out of there. And then I also want to enter in the initial state matrix, x0, because we need that, remember? So going back to the matrix menu, we're going to edit, and I'll edit matrix B. And that will be a 2 by 1. And we had 100, 100 and 900. Cool, cool? All right, so let's quit out of there. And then now we want to check out what's going to be happening, right? So we said, going back in the matrix menu and getting our transition matrix, which was matrix A, right? And then I'm going to set it up to go to powers. So raise to the 1 power, right? We'll redo the first one. And then times second matrix B, enter. And notice we got our 110 times our x0 matrix. Cool so far? Now, if you hit second entry, you'll get what you just, plugged in there. And I want to now square my transition matrix, and lo and behold, we got 11189. Now, in order to get what's called your steady state matrix, you just keep raising it to higher and higher powers and see where it levels out. And that gives you your steady state matrix. So here, okay, let's do this again. Now let's go like to the 10th, right? And look at that. Do you see that as you get larger and larger and larger, and you don't think about partial mice, you're gonna actually tend towards our x1 that we got, which was the transition matrix squared times our initial state matrix. So just for fun, let's do that again. And now let's raise this to the 100. And look, do you see it's totally leveled off here? So it turns out that our part B gave us our steady state matrix. Isn't that groovy? Steady state matrix. All right, is 111,889 because of what we looked at here, right? Oh, actually, sorry, this was our A squared, so P squared times B was our 111,889, right? And then as you keep raising the powers, it really steadied to the same thing. Groovy? All right, so next up, I love weather stuff. So why don't you go ahead and try this next one on your own and see how you do, and then play the movie and check your work. Cool, cool? Okay, let's see how you did. First off, we want to find, okay, so, all right, let's see how you did. This example states, it has been claimed that the best predictor of today's weather is yesterday's weather. Suppose that in San Diego, if it rained yesterday, then there is a 20% chance of rain today. And if it did not rain yesterday, then there's a 90% chance of no rain today. So we want to find the transition matrix describing the rain probabilities. Cool, cool? All right. So P equals, so we have rain, we have no rain. Rain, no rain. Cool, cool? All right, so let's see what all we were given. So, if it rained yesterday, so it was in the rain state yesterday, then there's a 20% chance of rain today. So we were given rain, rain in the intersection, right? So if we have rain, rain in the intersection, it's going to be what? Over here, right? So we'd have our 0.2. Cool so far? All right. Let's look at the next one. The next one we have, if it did not rain yesterday, there's a 90% chance of no rain today. So no rain intersect no rain is going to be down here, right? And that one is 0.9. Cool, cool. Now to make the column sum to 1, we'll have 0.8 here and the second row, first column. And then in the first row, second column, we're going to have what? Beautiful, 0.1. Okay? It either rains or it doesn't rain. Okay? So this one, it's sort of like an so easy it's hard thing. So we're going to do 1, 0, where this will be rain and then no rain. Okay? Good so far? Because you got to start somewhere. So let's take a look at what happens, right? If it rains Sunday, what is the chance of rain on Tuesday? So Tuesday is 2 days later, right? So what did we learn last time? Beautiful. This is going to end up being P squared times x0 equals what? We can just do it by hand, I guess. So we'll have 0.2, 0.1, 0.8, 0.9 times 0.2, 0.1, 0.8, 0.9 times 1, 0. And that's going to give us 0.04 plus 0.08 is going to be 0.12. And then 0.02 plus 0.09 is 0.11. 0.16 plus 0.72 is going to be 0.88. This looks awfully familiar, doesn't it? And then this one is going to end up being 0.89. Isn't that weird? Did I do that on purpose? Our last problem ended up having the same situation. I'm sorry, I didn't do that on purpose. All right, and then now we're going to have to multiply that by our x0 matrix. And so, by the way, from this, we're going to, I'll do it at the end. From this, we're going to get our x2. All right, we're going to skip over x1 and go straight to x2. So, this is going to end up being equal to 0.12 plus 0 is 0.12, and then 0.88 plus 0 is 0.88. Cool, cool? And that's equal to, good, x2. So, if it rained, on Sunday, There's A. %12 chance of rain on Tuesday. Cool, cool? All right, now let's look at this next one. Well, if it did not rain on Wednesday, what is the chance of rain on Saturday? Okay. Well, here we go. What are we going to have to change? Do you see the P matrix is going to stay the same, right? Because those probabilities don't change. And let's see, how many days is going to be between them? So Thursday, Friday, Saturday, right? So you're going to be cubing our transition matrix times, well, x0, but we're starting with no rain, right? So this one that we did up here, right, is showing that it rained. So this is the one, maybe instead of x0, we could call this XR for the rain probability. So that would be XR. And then there'd be another X for no rain, right? And what would that be? Beautiful, 0, 1, where you would have rain, no rain. Cool, cool? All right. So we would have to use the NR one. So what we're going to do is we're going to take our transition matrix and we're going to cube it. We'll do this on the calculator. And we're going to multiply that to this one here because that's going to show that, hey, it didn't rain. We're doing the one where it didn't rain. Cool, cool? Fortunately, we have the same transition matrix, so I'm just going to change B, okay? So we're going to go into the matrices, and then we're going to go to edit B, and so this one we're going to put 0 and 1. Cool, cool? All right, so second quit. Now I'm going to go ahead, I can do my I'm going to clear these and then I'm going to go second entry. So remember A corresponds to the transition matrix P. And here, what do we have? We wanted to cube it, right? And that gives us 0.11 and 0.889. Okay, so if it did not rain or didn't rain on Wednesday, there's an 11.1% chance of rain on Saturday. Cool, cool? Okay. Now let's look at something that's, a little bit more realistic. So, and I'm also going to take out these right here since we're kind of utilizing different models for our initial states. So here, what would our initial state matrix change to for part D? We'll call this X0, okay? So for this one, remember you're doing rain, no rain. We can do rain, no rain because it won't matter. We changed our probabilities. And so we'll have this says it's 30% chance, right? So 0.3. So that would make this one 0.7. Cool so far? If the probability of rain today is 30%, what is the chance of rain tomorrow? Well, it would first have to rain today, right? And so assuming that it rains, let's see what we get. We would get our P, right, times this x0. And then that would be 0.2, 0.1, 0.8, 0.9. And then our new x0, which is 0.3, 0.7. And so multiplying that out, what would we get? We get 0.06 plus 0.07, so 0.13. And then 0.24 plus 0.63 is going to give us 0.87. Cool, cool? So what's our answer? If the probability of rain today is 30%, there's a 13% chance of rain tomorrow. Cool? Okay. I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And if you like what I'm doing, please subscribe and tell your friends. Bye.